Hello, everyone. Sorry about the slightly late start here. I just wanted to make sure I had everything set up correctly. I'm hoping that everything's going well. I think the YouTube actual dashboard was a little screwed up there for a second, but um, it looks like it's just messed up when I have the uh, screen and split screen. So I won't know exactly how many people are in the stream because of that, but we're going to go on anyways. So first off, I just wanted to mention that I am past the whole bulk of tests, so I do plan to do a little bit more work on my physical projects, whether that be on the AI or uh, on the comics and any other projects, whether it be musical oriented. It's kind of just how I feel in the moment. So I'll be letting you know about those on the Wednesday streams and on these brief updates in the beginning of the streams. You may notice that there's some different kind of stuff thrown around behind me. We are doing some renovations on this room to hopefully get it to its final state, which I know I talked about when I moved in to this room originally, was that this was a temporary setup. I'm eventually going to be over in that corner on a desk, and so it'll be a completely different angle. It'll just look like a different room to you guys. But that I don't want to linger too much more on the actual just random topics and projects that I'm working on. I want to get into the bulk of the stream. So I am pretty excited for this stream. I've been doing a lot of thinking about it. So you'll see the title is a little bit ambiguous because I like to mix the topics together, but I am going to be talking about two topics today. The first one being slang units of measurement, and the second one being the vector, the analytical method using vector notation in order to solve four-bar linkages. So we'll see how long the first one takes. I might save the second topic for later, but we'll see how it goes. I'm going to get some things set up, but I'll be right back with the first topic. Okay, sorry about that. I'm hoping the mic is still working. It looks like it is. So we're going to move right into the first topic. So this is slang units of measurement. So I have it on full screen, so I'm going to switch it over to where you can see the paint window. And now we will get right into it. So in our society, speaking in English, although there is definitely slang in every language, in English, there's a lot of sort of ambiguous units of measurement that we use. And so, first off, I want to warn any of the younger audience, this is going to be somewhat of a more older, mature topic, I guess. So, let's get right into it then. So, what I'm going to be focusing on today is majorly categorizing and sort of putting a picture on the abstract units of volume that we use in our everyday life. So these units of volume are crapload, crap ton, and whatnot. So I'm going to be sort of just giving a general idea of what these are. So let's just list them off. We have a crapload, or a crap ton. I'm considering these to be the same thing, a crap load or a crap ton. Then we have a shit ton, And of course, after that would be a fuck ton. And so these I would claim are increasing in size. And remember, I'm talking about volume here. So these are things that people use a lot in their everyday life, everyday conversation. Maybe some people don't use the exact same language, but essentially they're the same units of measurement. So what I have decided is that I'm going to put a general, maybe not exact, but a general volume for these individual measurements. So I'm going to clear this off, and we're going to start with the first one. So we have Crapload. Um, so we have to think about what this actually describes. So if we have a crapload of something, then this usually means that this is it's a it's something you can count. It's not necessarily a liquid. I guess you could say you had a crapload of water, but in that case, you would normally be saying that you had a crapload of water bottles or a crapload of glasses of water. So we're going to assume that these are volumes of objects that you can count. So this is a little bit different from our normal measurements of volume, which would be gallon or liter, depending on where you're at. So these measurements are exact amounts of space that would usually contain like a liquid or some sort of very fine object. But in this case, we're sort of quantifying an object based off of how much space it's taking up. So what I'm saying is that a crap load is enough to fill up a sandwich bag. So we have a sandwich bag. Now, this doesn't work in all cases. So we have our sandwich bag. It has the little plastic strips on it to connect the bag together and seal it. So I'm gonna have some variations of this. So the first definition, this is number one, is to it is enough of something to fill up a sandwich bag. And like I said, this doesn't work for everything. So this would work for smaller objects like Cheetos or I'm missing an or perhaps pennies. You could have a crap load of pennies. Um, but this doesn't really work for larger objects. And so I want to sort of put a double definition here. So we're going to have a second definition. And this is going to be at least 12. So this, in terms of everyday speak, would be a dozen, or perhaps you could speak in dosnal. This would be dough of the object. So you're going to see a theme with that moving on. But what's nice about the number 12 is that it's very divisible in terms of breaking up objects into individual groups. So if you had 12 eggs, you can have a third of that dozen would be 4 eggs. That's a nice even number or nice benchmark number. You could have a fourth of those eggs. That's 3 eggs. You could have half. That's 6. You can have a sixth. That would be 2, or you could have a 12th. That's 1. So there's a lot of numbers you can work with without having to get into fractions, and so that's pretty nice in everyday speak, especially with things that can't really be broken into fractions. Like eggs would be a little bit difficult. You'd have to sit there and measure out how big one egg's worth of goop is and then divvy it up. So this is what Jono is claiming is a crap load. So Jono's crap load. So we're going to move up a step here. And so the next step from a crap load or crap ton is a shit ton. And so the trend is that the more vulgar the language, the larger the amount of objects. So this would imply that there is a significant amount more than the initial setup. So we have a crap load, which is about 12, or perhaps a sandwich bag for smaller objects. We're going to continue the trend with that to be a gallon bag. So we're going to have a bigger bag, and so this is something that you would normally store leftovers in. It can store a lot more than just one meal, we would say. This first definition also allows you to apply this to some things that aren't as countable. So if you had some sand, I guess, then sand tends to be seen on a macro scale as opposed to individual granules. So you could have a shit ton of sand, and it would just be a gallon bag full of sand. So that's what I'm saying is our first definition. And so this is completely full with whatever object you are desiring. And of course, we need a second definition for larger objects. So we're going to follow the trend of 12, and we're going to go greater than 12 squared, which is equal to 144, or 1 grow if you are following the Dosnell trend. And once again, 144 is very divisible, so it has all the divisors of 12, along with many more as 12 is multiplied to be larger numbers. And so this allows us to divvy up amounts into smaller groups that are still whole numbers very easily, as opposed to 100. If you tried to divide it by 3, that wouldn't really work, whereas 144 will do that fine. So a shit ton is what we're defining as either a gallon bag full of, or 144 or greater of an object. So you could have a shit ton of tanks. That would be a lot of tanks. You could probably take down a couple cities with that. Simply by rolling over it. I don't think you'd even have to fire the guns at that point. Okay, so we're going to move on up. And so we have a crapload or crap ton and a shit ton. And then after that, we have a fuck ton. Following the trend, this is slightly more vulgar. And we would say that this is a significant amount more. Well, you might be able to guess where I'm going, but I'm just going to say it anyway. We're going to get a 10-gallon trash bag of this. Now, this isn't necessarily our 12 jump in terms of volume, but we will continue that trend in the second definition. So we're going to get a nice big old trash bag, and it will have our tie over here and our tie over here. And so you can imagine if you had a fuck ton of pennies, that would be a lot of pennies. 10 gallons worth of pennies. I don't know if anyone wants to try and do the math on how much money that would actually be worth, but it would be a significant amount of money, although it would also be significantly heavy and very much a nuisance when you brought it to the bank for conversion to actual usable currency. If we keep going to our second definition, we can continue the trend of 12 to the 3. I'm blanking, and I'm going to have to pull out my calculator for this. It is 144 times 12. So 12 times 12 times 12 equals 1,728. I knew it was a 1,7. 1,728 objects. And so you can imagine that if you put pennies into a 10-gallon trash bag, there would be more than 1,728. But if you had perhaps, helium balloons that were inflated, you couldn't really fit 1,728 balloons into a trash bag. But if you wanted to have a fuck ton of balloons, you would have to go up, and I mean up as in the movie. You would have to have a significant amount of balloons. I don't know what the upward force would be generated by 1,728 helium balloons due to buoyancy, but you can figure that out in your free time. Now, there is something I want to mention that is a little bit interesting about the slang units of measurement, units of volume. Now, in real scientific and empirical measurements, we have the empirical system, which is a little bit frowned upon in the science community, and the metric system. And what's interesting is when we have the conversion of the equivalent metric unit to a empirical unit, we actually see that most of the equivalent units of measurement are smaller on the metric side than the empirical side. So in empirical units, we have an inch as our sort of small base unit, and that would be a centimeter in metric, but this is actually, it takes about 2.54 centimeters to make an inch. Moving up from that, there's a foot, and people may not know this, but there's actually a decimeter. It's 10 centimeters, which is significantly smaller than a foot. So the one exception that I can think of off the top of my head is that a yard is actually smaller than a meter, which is 100 centimeters. But that's kind of cheating because there's 36 inches in a yard and there's 100 centimeters in a meter. But that's just how the metric system works. It's base 10. So this is the special one. And then we have obviously a mile, which is significantly larger than a kilometer, and so on. This continues into volumetric units. So if we have a gallon, this is larger than a liter. A liter is actually a decimeter cubed. So that's a fun fact for you. But you see the trend, so that the metric system based units tend to be somewhat smaller than the empirical system's base units. So what's interesting is that this isn't necessarily true in these abstract units of volume. So if we have a shit ton, then we've established that this is about a gallon bag, or at least 144. But if we have a metric shit ton, then the interesting idea is that because this is more words, it actually seems as though it's emphasizing how much there actually is available. So I would claim that a metric shit ton is exactly 1.2 times a shit ton. And so this is a 20% increase, or a baker's dozen. It's also 1.2. That's actually just a coincidence when I was thinking this out. But this would continue into a metric fuck ton or a metric crapload. Although metric crapload doesn't really have the same ring, I would suggest a metric crap ton because a metric ton is an actual thing. So metric crap ton seems as though it would be an actual thing. So this is my general categorization of these abstract volumes, and so what I want you to do is to spread the awareness, because I feel as though people use these so willy-nilly that they don't necessarily understand what is the actual amount, and it tends to be somewhat of an exaggeration when they use these units of measurement. But I think, being the engineer I am, it's important to have standards, and even with abstract concepts such as a metric shit ton, there should be a standard, or at least a range of understood value to those words. So that is what I'm getting at. And there is one more unit of volume I want to mention. This follows the trend of units of volume that actually measure numeric value. This is a canoe. And you may say, that's not a unit of measurement, that's a boat. Well, it is a man-powered boat, and it is generally about the same size every single time. So now there are some differences. Sometimes you have 16-foot canoes, maybe even longer. If you get to the dugout canoes that the Native Americans use, they can be extremely long. But generally, we're talking about our I'm going to go to a campsite and rent a canoe for the day kind of canoe. So if we have a canoe of people, then how many people would that be? Well, a canoe, in terms of people actually paddling, would be about two people, but a canoe can also hold a couple more passengers. So, comfortably, a canoe could have three people in here, where two people are in the seats and one person is being the lazy bum in the middle but does not have a seat, so they are slightly less comfortable. It's a reasonable trade-off, but if you really want to push the um, possible carriage of a canoe, you could throw another person in here. Now, the warning labels will probably tell you not to do this, but it is possible. The canoes have a reasonable factor of safety in terms of flotation because of these air pockets up in the front and back. You can actually fill the canoe completely with water, and it will still be paddleable to where you can bring it back to shore. Um, so if we say that a canoe is about 3 to 4 people, then we can use this in the similar way that we would use our other abstract units of volume. So a canoe worth of PB&J sandwiches would be probably a metric fuck ton of PB&J sandwiches. Actually, I want to take that back. It might be about half a metric fuck ton of PB&J sandwiches. If you had golf balls, I would say that would easily be a fuck ton, if not a metric fuck ton, of golf balls. So you get the picture here. This is something that you don't necessarily need to raise awareness for unless you actually feel necessary, but I feel as though a canoe would be a very interesting abstract unit of volume. There are other units of volume that have been used in the scientific community. I saw that Randall Munroe on XKCD actually measured the volume of I'm sorry, I'm like the volume of the rockets that have been to space with horses. I think this was a jab at the idea of claiming that something has horsepower, even though it's a very it's a very specific number now and not actually the average power of a horse. But it was saying that he was saying that you could measure other things with having horses as your base unit. So that's all along the same vein. This is the general topic that I wanted to talk about for abstract units of measurements, and I think I'm going to be moving into my second topic, which is the 4-bar linkage using analytical method or vector method, as I would say. So if that interests you, keep watching. I'm going to have a random drawing at the end, so stay tuned for that. But if you've been watching this far, I want to thank you guys for coming out. I think that YouTube is actually glitching up a bit. It says that we have a couple people in, but when I have it in split screen, I can't see who's in and who's not. So I'm actually, I think I can do that. I can pull this over here and pull this over here, and then this one will be full screen and that one won't be. That just means I'll have to look to the side to check out the chat. So I see the mic is still working, and we're going to be moving on to my second topic. So let me clean the board here and take a drink of water. Okay, so obviously if there's any questions from the previous topic, I'll still answer them if I see them come up in the chat, but other than that, I will be moving on. So the second topic I'm going to be talking about today is vector method, for 4-bar linkages. And so I need to establish some basics here. And this is actually a rather um, uh, high-end college topic. Not necessarily master's degree or anything. I'm still a junior in college right now, but this is something that you learn in the engineering track. A lot of people don't even go that far into it because it's actually an elected course for my specific track of mechanical engineering, which would be the actual vein which would take on this daunting task. So I'll go over some of the basics because I wouldn't imagine too many people know what I'm talking about just right off the bat. But a 4-bar linkage is actually a combination of 3 bars, but it's kind of a little bit abstract. We think of the ground as the 4th connector. So there's this imaginary bar here that's connecting the 2 joints that are grounded. So we don't necessarily need this bar because the ground is holding the 2 joints in place. But what this actually is it's a 1 degree of freedom system. And what that means is that if we move any of these pieces, then all of the other pieces will move exactly according to some formula. So if we were to send this guy moving in this motion, you can imagine that this guy would rotate with respect to this point, and this guy would go this way as well, eventually reaching some point where it can't go any further. Now there are some special ones where there's a tiny linkage over here, and then we got a bigger linkage, and this guy goes back and forth here, and then this guy spins around in circles. So that's a crank, and then we have a rocker, but we're just talking about 4-bar linkages in general, and so this isn't anything specific, so we don't really need to get into the vocabulary. But the key idea here is that there's 1 degree of freedom, meaning that all of the pieces move together regardless of which one is the one we're actually moving. So whichever one we put force on, the other ones will move as expected. Now, if we add a 5th bar in here, that would actually ruin that idea. So if we had another bar like this and a connector here, then this could fall down due to gravity. It could whip up, and so it's hard to predict this, and we would actually have to be moving 2 of the bars with force in order to predict the position of this. So that's the basics on a 4-bar linkage, and I want to give some basics on vector notation. I did actually go over this a little bit, the Euler method, when I was talking about higher powers, and that's not a religious question. That's if we have a question of or it's a higher roots, I guess. So if we had the 4th root of 6, then you can use vector notation to find all of the roots of that number based off of the unit circle. And so if you want to look more into that, I'll put a link up in the corner to that video when I'm done and editing this. But essentially what the vector notation is if we have our 4-bar linkage, so we have some random configuration that just happens to look exactly like the last one I drew because it's the quintessential 4-bar linkage, then essentially what we're doing is we're saying that each of these linkages is a vector. So we're going to say that this is a vector, this is a vector, this is a vector, and then we're going to have one last vector coming from here to here, Now these vectors can go in any direction. Having these two coming out of the grounded point actually helps out a lot, just because it's not a relative position, but I'll talk about that a little bit in a second. I'm actually going to draw this with different colors so that it stands out a bit more. Um, I know that's a little bit sloppier, but um, I want you guys to see where the vectors actually are. So we have to write an equation for this vector loop. So first off, that requires us to decompose a vector. Well, not necessarily decompose a vector, but to represent a vector with a notation. And so what we're doing is we're actually going to just write out some things. So we have the length of this is going to be A, the length of this is going to be B, the length of this is going to be C, the length of this is going to be D. So we'll assume that we know these things. And also, we will have the angle here. This is going to be theta 2, actually, because this is link 2, but we're calling that A. This is just kind of general notation, so you can imagine that there is a theta here, and this will be theta 3. And then our last one is going to be from that vector to the ground. That's going to be theta 4. And so there's a theta 1 here, but we're going to start out with an easy case where this is actually a straight line, horizontal. So that theta is going to be 0. So we'll just keep this off to the side. Theta 1 is equal to 0. So like I said, we need to write out these values in terms of something that can be written out into an equation. And so if you know how to create things in vector notation, essentially what we're doing is we're using complex numbers. And so that may scare some people away. But essentially we're plotting things on the plane where the vector begins at the origin, and the horizontal axis is the real numbers, and the axis up here is the imaginary numbers. So imaginary means that there is a component j, and if they're pure imaginary, then there's only a component j. A complex number is the number a plus bj. Some people use I. That gets a little confusing in some engineering applications, so we tend to use j just because it stands out a little bit more to the little i's. This actually is very important in electrical engineering because I usually tends to stand for, I believe, current. So what we're doing is we're decomposing the vector. So we can imagine that our vector here is of length A at an angle theta. And what this actually means is that this vector is a e to the j theta 2. So what this is it's the Euler form of this. This can be decomposed into a cosine theta 2 plus a j sine theta 2, because j is the y, or the upwards direction, or vertical, I guess, because it can be down. And this coincides with sine being the vertical component of this vector. So we can write out this whole equation because this is an equation. If we consider this a loop, we can actually say that this comes back to the exact same spot. So in terms of vectors, it's equal to 0. So what we're essentially doing is we're following this loop, and if we're going along the vector in the direction that the vector wants to be going, which means the arrow's pointing that way, we say that it is positive, and on the contrary, if it's in the other, if we are going against the vector, then it's negative. So first off, we're going to start here at this point. We'll call this O2 and this O4 just for reference, for origin. So we will say that A times e to the j theta 2 plus, and so we're going to have our vector B times e to the j theta 3. Okay, so we're here. Now we're going backwards in accordance to this vector. So we're going to say minus c e to the j theta 4. And then once again, we're going backwards. So we're just going to say minus d. We can write this in just j to the 0. And so anything to the 0 power, it doesn't matter what this j is because anything times 0 is 0. Anything to the 0 power is 1. If you didn't know that, then there you go. And so essentially what we're saying is this is just d. I can actually erase that because I have an eraser. And so this whole thing is equal to 0. And the cool thing about this is we can use this to solve for pieces of information we don't have. So let's say that we knew how long all of these linkages were, all these links were. So we know how long A is, how long B is, how long C is, how long D is, and we're orientating this vector or this linkage A in such a fashion that it is creating this angle theta 2 with the horizontal. So what do we not know then? Well, we know A, B, C, D, and theta 2. We also know theta 1 just because of the orientation of how this works out. It's equal to 0. So there's two things we don't know, and that's theta 3 and theta 4. So, like I said, this is a 1 degree of freedom system, which means that if we know what orientation link 2 is in, or linkage A, then we can figure out what orientation all of the other linkages are in. So the way that we can do this, and you may be thinking, we only have one equation to work with. How can we solve for two different variables? The way that we do this is because this is a vector equation, and as you can see up here, this equation can be decomposed into different components. So each of these terms can be decomposed into its length times cosine times the angle added to its length times j times sine of its angle. And what I'm going to do is, well, the way we handle this is because half of the pieces of the equation will have a j in them, and the other half will not. Now, imaginary numbers and real numbers cannot be added together normally, like real numbers can be added to themselves. So essentially what this means is that both the pieces that have a j in them and the pieces that don't have to add up to be 0. They can't add together to be 0 because they don't add together. One's imaginary and one's real. So what we do is we actually split this up into two different equations because of that. We know that a cosine of theta 2 plus b cosine of theta 3 minus c cosine of theta. Oh, sorry, I forgot. There's a c in cosine, so I just started writing cosine. C cosine of theta 4 minus, and so this is actually important. I'm going to rewrite this in j to the 0. We have to remember that that this is actually here because the d is only going to apply to the cosine situation because the cosine is the horizontal component of all these vectors. Now, if you think about it conceptually, this actually does make sense because in order to stay at this point or end at this point, I guess, all of the horizontal components have to add up to be 0. So if we're saying that we're going to go cosine of A, or cosine theta 2 times A, then cosine theta 3 times B, we're here at the horizontal position of this point B we're going to call this big B and call this big A. And then it's going to be minus our horizontal component of C. So we're going to get to here to O4, and then we're minusing D, which brings us all the way back to O2. So this works out. And the same goes for the vertical components. Now, I'm not going to be writing the J in here because what happens is since all of these components have a J in them, and they're all set equal to 0, that J actually pulls out and is divided. Well, obviously, if you say that everything's equal to 0, you can divide both sides by J. 0 divided by J is still 0, so nothing happens, and you have the exact same equation. Not necessarily the exact same, but the relationship is still there. So C sine theta 4. And we remember, we don't have this D component in our second equation. So we have two equations. Both equations contain these values we don't know, which are theta 3 and theta 4. Now, these don't have to be the values you don't know. You could be given these values and try to figure out perhaps what the length between the 2 points are. And so this would be pretty easy, actually, because what can happen is you can just bring this D to the other side. You have an equation equal to D, and then you just need to find whatever else you're looking for from the other equation, and you can plug it in and you'll get D as your answer. But the power of this vector form is that you can solve for two things. Now you can do this graphically. It won't be exact, assuming that you don't have an infinitely accurate protractor, or perhaps you are slightly off when you're drawing things. But this method is exact, and that's the beauty of it. So assuming that your given values and your assumptions are correct, you can solve for two different values at the same time due to the systems of equations. So this is very powerful. But what's interesting about this is that this vector formation can actually be used to find velocity and acceleration. So I'll show you what I mean by that. So I'm going to clean things up here, and I'm going to rewrite the original vector equation. So we had a e to the j theta 2 plus b e to the j theta 3 plus c e to the j theta 4 plus d e to the j theta times 0 is equal to 0. So this is our position equation. And so this is our original vector loop that equals the position. What's interesting about a 4-bar linkage is that when you look at the velocities of the individual points, these velocities are actually the, or I guess you could say the angular velocities, but the velocities add up vectorially in order to make a polygon. So this is an important piece of information, but this can be completely ignored when you're using the analytical method. What you can do is, since this is the position equation, if we normally had a position equation of s is equal, or s of x is equal to, I don't know, x squared, what would we do to find the velocity of this position equation? Well, v of x would be equal to the derivative of this. So that would be 2x, and then our acceleration would be the derivative of the velocity, which would be 2. And we can use the exact same method. So if we just clean things up here, sorry for the delay. What we can do is we can say that we want to take the derivative of each of these pieces. And so it's nice because they're a linear combination. We can just take the derivative of each of them, add them together, and we get the derivative of the whole thing. So the derivative of this piece, and so first off, we're going to assume that none of these linkages are increasing in length. That's important for this case to keep things simple. So If this a is a constant, then all we're taking the derivative of is e. And what's nice about e to anything is that the derivative of that is e to that same thing times whatever the derivative of the thing in the power is. So we're going to say that this is actually, if this is our independent variable, then we're going to have a j e to, oh, actually, sorry about that. So we have to take the derivative of theta. And so the derivative of the angle is the angular velocity, just like the derivative of the position is the regular velocity. So this is going to be a j omega 2 e j theta 2, omega being the angular velocity. So if we had our vector here, this would be the rate at which the rate in radians per second at which this vector is changing. So that's one term plus bj omega 3 e to the j theta 3 plus c j omega 4 e to the j theta 4. And this last term is completely constant. Like I said, nothing is changing in length here. So the derivative of d is 0. The derivative of e to the j 0, which is 1, is 0. So we don't have anything else in this equation. We've actually reduced our equation down to 3 terms. Now, these 3 terms are relatively complex, not to make a pun here, but they are a little bit easier to work with than having our 4 terms. So let's look at what we're working with. We've already figured out what theta 3 is and theta 4 are from our position analysis, and now we have a new vector equation. So we can then again solve for 2 different things. So let's say, since we're controlling our linkage A, we can actually adjust the value of what the omega 2 is. Well, that only leaves 2 things we don't know. That's omega 3 and omega 4. So once again, and I'm not going to write it out just for time's sake, but we can decompose this into sines and cosines. Now, there is something interesting I want to point out. We have to remember that e to the x to the jx is equal to cosine of x plus j sine of x. So we have to remember that this is what we're working with. So then what is j e to the jx? Well, that just means we're multiplying this other side by j. So if we multiply cosine by j, we multiply this sine term by j, that gives us j squared. So j times j, this is just imaginary number times imaginary number. If you're up to date on your imaginary numbers, you know that an imaginary number times an imaginary number is just makes -1. So if you take the unit imaginary number and multiply it by itself, it gives you -1. Because the way that we define imaginary numbers is that j is equal to the square root of -1. So if we square j and square this side, we get -1. This new term, we can actually take this j out of here when we decompose it and actually switch up which side has the j and which side has the real numbers. So this would actually be j e to the jx is equal to negative sine of x plus j cosine of x. And this actually makes sense when you think about it graphically, because if we have our vector here, and this is our linkage, we want to think about what the velocity of this vector is. So if we have our omega 2 going in this direction, the velocity of anything rotating about a fixed point is exactly perpendicular to the radius created by this vector. So this is perpendicular, which means that it's it's going to be that the horizontal direction is going to be actually 90 degrees offset, and in this case going in the opposite direction. So that's why we have this negative. And the vertical, or I might have said that backwards. So the the horizontal component is going to be offset by 90 degrees because of this j, because we're actually switching sine and cosine, and it will be in the opposite direction. And then the vertical component will actually also be not offset by 90 degrees because now it's cosine, and it's going to be in the same direction for the velocity. So we have you have to keep this in mind when you decompose it. So actually the equations will be kind of flopped. But this doesn't really affect too much because this negative is going to be able to divide out since it's equal to 0. And this j is going to divide out since it's equal to 0. So essentially it's about the same equations. It does get a little bit more interesting when we go to acceleration. So I'm going to move on to acceleration. Actually, let me just grab this equation for time's sake. Copy that. And now we're going to clean the board here and paste that guy back in. So you have to remember, this is our velocity equation. If we want acceleration, we then have to derive this again. And so that's not too difficult. It gets a little bit more confusing, though, because this omega can actually be, it is actually derivable. So it's not a constant value. It's something that we can change because it's the angular velocity of our independent variable theta. So each of these components, when we take the derivative, is actually going to have two different components. This is due to the chain rule because we have a differentiable value multiplied by another differentiable value. So we're going to first differentiate the first term and multiply it by the regular second term. So this will be aj alpha 2, so this is the angular acceleration, ej theta 2 plus a, and so remember that we're not touching e, so all the other constant values stay the same. But here we're differentiating e to the j theta 2, which in the velocity, you'll remember, took a j down. So what we're actually going to do is that is going to be multiplied by this other j and become a -1. So we're going to have negative a omega 2 squared, because we're differentiating this theta 2 again, e to the j theta 2. So this is going to be done for all of this. And actually, this was supposed to be subtraction. I think I wrote that incorrectly when I was doing that before, just because of the way we were oriented originally with our original problem. So this is how we're differentiating these two terms. And so this is actually interesting because it claims that there's two different things determining the acceleration of this point. And if we think about that graphically, then it actually does make sense. So we're going to have a term that is perpendicular, because we remember that this multiplication of a j does this. So this is going to be our first term right here. And we're also going to have another term which is going to be in the direction of the position, but negative. So from this point, it will actually be down. And I'm going to grab another color here. So we're going to have another vector here. And imagine this is a 90-degree angle. So what does this mean? Well, it's saying that there's always an acceleration towards the center. And if you think about that with any circular motion, this is true. If you have something that is on a rope and you swing it around, it doesn't accelerate away from the center. it stays on that circular path, but in order to, if it's going straight, it wants to go tangentially, and there's a force that's pulling it to curve it around at the exact same radius, which means that there is a force applied, and F equals ma. So that means that there is actually a acceleration towards the center of a rotating body, a body rotating around a point. So there's always going to be this acceleration that I've written in red going in towards the point. And what's interesting about the vector notation is this right away tells us that this acceleration is actually due to the angular velocity and not due to the angular acceleration. So we have another acceleration, which is actually how it's the change in the angular speed. And so this makes sense. If we're putting a force on it this way, it's going to want to whip faster than it already is. And then we have the second term, which is pulling it in towards the middle, which means that it stays on a circular path. So this is true for all of the points. And so what we find is that we can then we know what all the omegas are, we know what all the thetas are, we know what all the linkage lengths are, and we can solve for the alphas, assuming that we know the acceleration of at least one of them. So this means that we'll have an alpha 3 and we'll have an alpha 4. So this is vector notation, and it's very powerful. This is what people use to program computers for simulations. Now, there is a little bit of simplification for specific situations. Like I said, there are different orientations of 4-bar linkages, whether they be crank sliders, crank rockers, double rockers. I don't think there's any double. Actually, there is double cranks, but they're kind of stupid. But you can solve this out once, plug it into a computer, and then every time, all you have to do is give it the position of this vector, and it'll tell you where all the other vectors are right away, because there's just a simple equation that it has to solve. And like I've said in the past, computers are very good at solving equations. So this is vector notation. Now, there are some interesting things. So like I said, in this case, none of the linkages are gaining length, or gaining or shortening in length. So if we just had, let's say that this guy was a slider that's 90 degrees with respect to this link, and it's sliding along this bar. So we can imagine that this is rotating, and then this guy slides in as that pushes out. Anyways, what we do is we actually, I'm going to grab blue. Just maybe, yeah, we'll go to blue. We can say that there's a vector here, and there's a vector here, and there's a vector here, and of course there's a vector here. And we'll imagine that that's horizontal, even though I've done a poor job of drawing that. So the difference with this situation is we have our A, we have our B, we have our C, we have our D, we have all of our angles. The difference is that B is changing. So B is not constant, and we now have to consider that change. What that means is when you differentiate the original B term, when we have e to the j theta 3, and we differentiate that, we have to use the chain rule here. So that means that we have our b dot, as we say. This means that it's the time derivative. So b's change with respect to time times e to the j theta 3. So you'll notice there's no j, there's no omega. And then this will be plus, so it'll be plus b, sorry about that, bj omega 3 e to the j theta 3. And so this is two terms, and you can only imagine it gets a little bit more confusing in the second in the second derivative. So I'll go ahead and write it out. So both of these have multiple terms that need to be differentiated with the chain rule. So it's going to be a long process. We have our b double dot, which is the it's the acceleration of of the length of b, or you could think of it as the acceleration of this rocker, essentially. Um, e to the j theta 3 plus b dot j omega 3 e to the j theta 3, and we're going to have plus, we're going to differentiate b first, so we'll have another b dot j omega 3 e to the j theta 3. Now these are the same thing, I'll get to that in a second. Plus we're going to differentiate our omega, so we're going to have our b j alpha 3 e to the j omega 3, and our final term I'm going to write below here is our inwards acceleration. So that's going to be b j, that's going to be omega, oh sorry about that, there is no j in this term because we've put the negative sign here because there's j squared. So that's going to be omega 3 squared e to the j theta 3. So what we have here is we have our normal acceleration, we have the acceleration of our slider here, and we have these two terms. And so this comes together to be 2b dot j omega 3 e to the j theta 3. And so this has an interesting name. It's actually the Coriolis acceleration. Essentially what it says is if you're here and you're watching this guy, it's going to have an acceleration perpendicular to its actual travel. And so this acceleration doesn't really exist, but it's something that you'll witness if you yourself are in a rotating reference frame. So essentially, let's say you had two people sitting on a wooden plank. I can draw this out actually. So if you have a ball here and there's a plank going across, you got Johnny and Johnny's got a ball, and then you have Sally over here. Sally's got some long legs. Sally's waiting to catch the ball, and this whole thing is spinning in a circle. Johnny tries to throw the ball to Sally, but by the time the ball gets to where Sally would have was originally, Sally's now over here. So in terms of Johnny's perspective, it seems as though, so we're gonna look down the perspective of Johnny's line of sight to where Sally was. It seems as though this ball we have is taking this curled path out to the side because he is in a rotating reference frame. You can try this on your own. You will get somewhat dizzy, and what essentially you have to do is you have to throw the ball here so that it curves to where Sally will be. So this Coriolis acceleration is there, but it only exists in a rotating reference frame. And if you want to feel it for yourself, get one of the merry-go-round things at a playground spinning really fast and try and run on it. When something hits you very hard in the side, that's Coriolis acceleration for you. So that is vector analytic notation, and so I hope this was explanatory and thorough, and I will be moving on to my random drawing. I'm sorry for those who were not as excited for a lecture on vector notation as I was, but we will get back into the fun stuff, I promise. So I'm going to take a few seconds to get everything set up, and we will move into the random draw. And if there's any questions, please feel free to leave them in the chat. All right. So, you know what time it is? It's random drawing time. I have my random number generator set up with 1 through 25 as the possibilities. We're going to get our first number. We've already gotten that. 3, which is board game as our noun. Our second word is play, musical in parenthesis. And our third word is exciting. So we are not playing a board game in the normal sense because we have to be playing it musically. So this is interesting. Perhaps we're not just having. So with board games, you don't normally play them on your own. This is a group activity of about 1 canoe of people. So that would, if you didn't catch the first segment, be about 3 to 4 people in a normal board game. Now you can have board games where there are just 2 people, whether it be checkers or chess, but we're going to assume that the majority of board games require about 3 to 4 people. And so what can we do with 3 to 4 people? Well, that's about the same amount of people in the average band. So what we can do is we can actually make a band out of people making music with a board game. Now this, I don't know about you, but it sounds very exciting to me. So I think the third one is a given. But first off, we have to lay down some percussion. So we're gonna have a callback for Johnny here. Johnny's gonna sit over here. He's a little bit more defined now. He might be working out so that he can play percussion better because everyone knows that you got to be ripped to play the drums, right? So he's gonna get a board game here. It's gonna be a foldable board game, so like the normal board games that we see, it will fold together, and he is going to apply a force, creating a angular acceleration of the board game. I guess he needs a face. That's probably important. But while I'm drawing this, he will be applying a force to either side. He can probably just apply it to one and wait for it to meet up with the other one. But this will smack together with this other side over here and shoot air out in all directions, creating a sound wave. And so if he does this repeatedly with a rhythm, then he will be the percussion section. I'm hoping I don't embarrass myself with spelling. That is a U, not a W, even though I drew 2 U's, I guess. But I'm going to leave it there for effect. So we have our percussion. Percussion's nice because it allows everybody to sort of get a feel for what the rhythm is and stay together as a group. So percussion is very important as a foundation. Now, there are some bands that have percussion as their main instrument, and I say more power to you. It is very impressive to see percussion stand alone. But it is extremely important, and you will know from my performances that I may not be the best with tempo. This might be helped if I had a drummer along with me, but drummers in an acoustic situation tend to be somewhat overpowering unless they were playing something like bongos, but I don't own any bongos. So that aside, we have a percussion section, and so we need to have perhaps some other instruments. We could go with a full percussion band just because that might be a little bit exciting, but I think it'd be nice to have a couple notes to work with. I'm trying to think of possible board games that would be able to apply that. Perhaps if we have, I'm trying to think of a board game that actually has this. But you know this is probably going to look a little weird when I draw it, but if we have the board game where there's some path going around and you're trying to get through that, that path. But in the middle, instead of having dice yeah, I guess it's plural, so dice. Instead of having dice out and about, they have this little popper thing. I'm trying to think of a game that actually has this. Um, Nothing's coming to mind. If you know any, leave them in the chat or in the comments later. But so we have our dice here, and it's actually a little popper. It's a kind of like a metal like little tab thing under it, and then when it pops down, it goes inverse and then comes back out. So essentially, it's a spring, and so we're gonna have Sally over here playing the popper, and so Sally, again, is somewhat defined. I guess she's been working out with Johnny. So Sally is going to apply a direct force on a point of contact to the popper. Um, and so she's getting into it. She got her head banging, I guess. So she's got some angular velocity, I guess. And so this is going to be giving off notes. Now, sometimes you can get a couple different notes um, out of basing where you push the popper. So we're gonna assume that we got a couple notes to work with on there, but it would take some precision. But I think Sally's up to the challenge, and so this can be our rhythm, and we just need to think of something that would possibly have a solo. So we may need to dig deep into the possible board games. Um, I don't know if we could go with some electronics. So if we have possibly the mechanical Monopoly, now this is somewhat heathenistic, but there are Monopoly board games that have credit cards. There's actually even better. I'll reference my girlfriend here. They have a Barbie shopping spree game, and apparently the batteries are dying on the speakers, so it sounds somewhat demonic. So that can be our vocals, I guess. So if we have our Barbie shopping spree, um, we're just gonna turn it on and see what happens. We don't even need anyone playing this. So we're gonna have our little speaker. I'm not sure what the actual orientation of the game is. Sadly, I have not actually played the game, but we're gonna have our little speaker here with a noise coming out and possibly some sort of satanic portal opening up in the background for mystical effect. Looks more like a door. But I think that we're starting to get to a normal picture here. I think it's pretty complete in satisfying what we are doing. And if this is not exciting for you, then please let me know how I could improve this picture. I know the audience has dwindled slightly since I talked about vectors for about 45 minutes. But I know that you still have it in you, so if you are watching this later, let me know how this picture could be improved. But I think this would be a pretty interesting band, so I don't know. Maybe if I get a little bit more support on here, I might try and put this together to actually make one of these bands just for a crazy episode. But that's completely up to you guys if you want me to do that. I think this is a complete picture, and I have hit an hour and 15 minutes. This is actually one of the longest streams I've ever done, and my voice is feeling it. But I feel as though I have been very thorough in all of my explanations today, so I'm happy with how it went. I noticed that one of Sally's arms is significantly thinner than the other. I won't mention anything further on that, but I want to thank you guys for watching. If you've watched the whole way here, this has been a long one. And I do plan on trying to get some work done on something by Wednesday, whether that be the AI. I do have some ideas I talked about in some of the past streams on how I could remedy the wall I kind of hit with that. But I'm going to leave that for Wednesday. So I want to thank you guys for watching, and I will see you